Hello there, Mr. Sutton here, bringing you the AB Calculus 614 Extra Practice Number 2 solutions on volumes with known cross-sections. For this problem, we want to find the volume of the solid described here. So the base of this solid is the region enclosed by this parabola and y equals 0, and cross-sections perpendicular to the x-axis are semicircles. So this is a calculator question. Let me take a sec to see what this graph looks like. So I've got this function here entered in my y equals. Let me just zoom 6 this thing and get a basic picture of what's going on. So we have this region enclosed by essentially the x-axis and this parabola, so this section right here, and we've got some semicircles coming out of this thing, sort of growing out of this thing, kind of into your face, as it were. So we want to find the volume of this solid that comes out of here. First, we need to get the area formula that we're going to be integrating across this whole region here. Since we're doing semicircles, the area of that is going to be, let's see here, pi r squared would be a whole circle. So semicircles, we've got 1/2 pi r squared. Now, to get the radius of these semicircles, taking another look at my graph here, the distance from the x-axis to the curve, which is basically this function right here, negative x squared over 9 plus 4, that's giving us the diameter of these semicircles. These semicircles are going from one end to the other of this shaded region. But I need the radius for this formula. So to get the radius, I actually need to take half of this function up here. So I'm going to write 1/2 times pi times 1/2 of all this stuff. And inside that 1/2 of all this stuff, parentheses, I'm going to square that whole parentheses there. So the 1/2 is getting squared along with all this other stuff. So this is my area formula that I'm now going to integrate. In terms of my limits of integration, I just need to see where this curve intersects the x-axis. And I mean, if you look at my grapher here, it looks like that's going to be -6 and +6. But you could solve it algebraically too. So setting that thing equal to 0, we subtract 4, multiply by -9, we have x squared equals 36. So yeah, plus or minus 6. So now let's do the integral for the volume here from -6 to +6 of this a of x that we just wrote, a of x dx. And now I'm going to do the rest of this on the calculator. To try to make things a little bit cleaner here, I'm going to put this whole a of x function inside y equals as y2, and then I'll just integrate y2 from -6 to 6. So let me do fancy fraction here, 1/2. So we've got a 1/2, we've got a pi, we have a parentheses with another 1/2 inside, and I could probably simplify this, but I'm just going to write this the way it is so that there's no chance I make any mistakes here. Open up, well actually we don't need to open up another fraction because what we're taking half of in here is just this y1 function. So I'll just do alpha trace y1, close that parentheses and square it, and that gives me this a of x. So quitting out of there now, let me do math 9 for integral. We're going -6 to +6. I'm going to do alpha trace y2 for the integrand, so that's a of x. And then I'll put an x over there next to the d, press enter, and we get about 40.212. So there we are. For this problem, I'm trying to find the volume of the solid whose base is the region enclosed by the semicircle given here and the x-axis. And we're told that the cross-sections of this solid are squares and we're perpendicular to the x-axis. So that tells us we're integrating from left to right to find the volume. So let me go on my calculator and graph this thing out just to see what we're looking at for the area. So I'm going to put that in y1, and I'll be using it later on anyway, so this isn't just a wasted trip just to see a picture. Let me zoom 6 this thing. So we have a semicircle, which it doesn't really graph as completely as you would expect, but it really does go down to the x-axis there. So we're basically have these squares whose base is the distance between the x-axis and the semicircle. And these squares are just kind of growing out of the screen. So the area of a square in general, that's going to be a of x equals s squared. Now the base of the square, the side of the square, is, again, just going to be this distance between the x-axis and the function we just graphed. So you could really just use this radical 16 minus x squared as one of the sides of your square. So if we just square this thing, that gives us the area formula for each of the cross sections of our shape. And now we're just going to add up all those square slices across the whole interval. What are our limits of integration going to be? Well, we've got this thing intersecting the x-axis, so we could see on the calculator where they intersect, but this is going to be pretty quick to solve anyway. So if I square both sides, subtract 16, divide by -1, we have x squared equals 16. So plus or minus 4 then for the limits of integration. So I'm doing the integral from negative to positive 4 of this a of x here that I just wrote. And let me do the rest of this on the calculator now. Now the way I like to do these problems is I like to put a of x as a y equals, so I can just take the integral of y2 from -4 to 4. It just seems cleaner to me. So for a of x, I'm just squaring this y function that we started with here. So I'm just going to do alpha trace y1, and now I just have to square that. And now let me quit out of there. I'm going to do math 9 for integral. We're going -4 to positive 4. Alpha trace y2, that's where I stored a of x. And dx, enter. 85.333 would be our volume for that shape. On this problem, we're trying to find the volume of a solid whose base is the region enclosed by this semicircle and the x-axis, and the cross-sections perpendicular to the x-axis are isosceles right triangles with one leg in the base. Okay, so let me graph out this semicircle. So I've entered the semicircle as y1 on my calculator. Let me do zoom 6. So there's our semicircle. Now we have some isosceles triangles coming out of this, and the base of those triangles is in the area here, is in this region. So in general, area formula for an isosceles right triangle, well, just for any triangle, is 1/2 base times height. And we need this because this is the area that we're going to integrate over the interval. But now for an isosceles right triangle with one leg in the base, well, that means that your base and your height are the same leg, if you just think of an isosceles right triangle. So that means that this is really going to be 1/2 base times base, or 1/2 base squared. So now we just need a way to relate the base back to this x here. So just taking a look at my graph, I think the visual helps here. Again, the base is in the base area here. So your triangle base is basically this distance between the x-axis and the semicircle. So we could describe the base of this triangle as really just the formula for this semicircle, radical 49 minus x squared. So I can just write 1/2 times this radical squared. And that's going to be the area of my cross sections. So now for my limits of integration, I just have to set this thing equal to 0 to see where it intersects the x-axis. So squaring both sides and subtracting 49, dividing by -1, square rooting, we can see this is going to be plus or minus 7. So for my volume, I need the integral from negative to positive 7 of this a of x that I just did, and I'll put a dx next to that. Let me just do the rest of this on the calculator now. To do this problem, I need to enter this a of x somewhere. I'm just going to put it in y2, and then I'll just integrate y2 from negative to positive 7. So I'm going to have 1/2, so a fancy fraction, 1/2 times, and now I need to do basically what I put in y1 squared. This is the base right here. So let me just do alpha trace y1 and square that. So I'm saving a little bit of rewriting here. And now let me quit out of there and just integrate that. So math 9 from negative to positive 7. So we got -7, positive 7, alpha trace y2. That's a of x really, and then dx over there. Press enter. We've got 228.667. For this one, I'm trying to find the volume of the solid whose base is the region enclosed by y equals 1 and y equals x squared, and our cross sections perpendicular to the x-axis are squares. Let me start by graphing this out. So I've got y equals 1 and y equals x squared in my y equals here. Let me do, I don't know, probably zoom 4 would be good enough on this one. Pretty sure these are pretty close together. So this is our bounded region, and we've got some squares that are apparently growing out of that. So I need the area formula for my cross-section. They said that was squares, so that's the shape I'm going to be integrating from one end of that base area to the other. So that's going to be an area of s squared. I'm going to write a of x equals s squared just to start with. But I do need to express this in terms of x. So looking back at my graph, how do the squares relate to the x values here? Well, since these squares are growing like vertically out of this thing, the base of each square is just the distance between y equals 1 and y equals x squared. This distance right here is giving me the base of these squares. So that means that this side of the square, I could express this as 1 minus x squared. That gives me that distance. So I've got then 1 minus x squared squared for my area formula. So that's what I'll be integrating. Now I need limits of integration. So I need to know where 1 and x squared intersect. If I set those equal to each other, then clearly this is happening at plus or minus 1. So my volume then is going to be the integral from negative to positive 1 of this a of x dx that we just wrote. And it's time for the calculator. So here's what all of this looks like on the calculator. I would normally enter the whole a of x function in y2 or something like that, but there wasn't really a whole lot going on with this a of x formula. You just have to be careful because this 1 minus x squared, that whole thing is also being squared. So integrating that now on the calculator, pressing enter, we end up with, that's actually a pretty small volume, 1.067. For this problem, I want the volume of the solid whose base is the region enclosed by the semicircle here and the x-axis. And our cross-sections perpendicular to the x-axis are, this is kind of special, rectangles with heights half that of the side in the xy plane. Let me start by putting this in my calculator and seeing what the base area, the base region looks like. So I've got this entered in my y1. Let me do zoom 6 here. So there's our semicircle, and we have rectangles coming out of this thing. So in general, my rectangle area, which I'm going to have to express in terms of x to integrate it, is going to be base times height, but that's not quite good enough yet. We can go a little bit further with this. They said that the heights of the rectangles are half the side in the xy plane. So basically, the side in the xy plane is this b here. So the height we can express is 1/2 b. So then we could rewrite this as 1/2 b squared. And I need to go a little bit further now because what does b actually equal in terms of x? Well, b is the bottom of the rectangle. It's the base. Now these rectangles are coming out of this semicircular region, and the base of each rectangle is basically the distance between the x-axis and the semicircle. That distance is given by this formula for the semicircle. So I can just write 1/2 radical 16 minus x squared squared. This radical here is the base of the rectangle. So that is my area formula. Now I'm going to integrate that. Before I can do that, though, I need my limits of integration. So where does this semicircle intersect the x-axis? Where does this thing take on a value of 0? Well, if you just think about this, 16 minus what squared would give me 0? Oh, positive or negative 4 squared. 16 minus 16. So we have x equals plus or minus 4 out of that. So then my volume is going to be the integral from negative to positive 4 of this a of x that I just defined up here. Don't forget the dx. And now I'll do that whole thing on the calculator. To make this a little bit cleaner, I'm actually going to define a of x as my y2 here. And then I'll just take the integral of y2 from negative 4 to 4. So it turns out that this stuff that's being squared is exactly my original function that I put in y1. So for y2, for my area function, I'm just going to write 1/2. So I'll just use my fancy fraction here. 1/2, and then I'll just do alpha trace y1, and then just square that. So that's 1/2 times the base squared. Quitting out of there now, I'm going to do math 9 to get my integral. We're going from negative 4 to positive 4. Alpha trace y2 brings up my a of x function I just created, and I'll put an x there with a d. Enter. Gives me 42.667. On this calculator-based problem, R is the name of the region in the first quadrant bounded by the y-axis, the x-axis, and this exponential graph, and the line x equals 3. This is the base of a solid, and for each solid, the cross-section perpendicular to the x-axis is a square. So we want the volume of that solid. So this is a known cross-section problem. I need to get the area of the cross-section shape here. Before I do any of that, though, let me actually just graph this out and see what our base area looks like. So here I am in my y equals. I'm just going to graph this out. And another reason I'm doing this is I'm going to have to use the calculator on this function eventually to find the volume anyway. So I might as well put that in there now. I don't know really what window to use. Let me do zoom 6. See what we're looking at here. Okay, I can get a lot closer apparently. Let me do zoom 4. So we're looking at the region enclosed by the y-axis, the x-axis, and the line, well, this is kind of interesting, x equals 3. So that line is all the way over there. In fact, let me just quit out of here, and I'm just going to do second draw and draw the vertical line. So option 4, vertical line, x equals 3. So there we go. Apparently there's a tiny little bit of space in there right before you get to 3, and probably after as well, because it's an exponential function. So yeah, this is the base area, and this has some squares growing out of it. So the area of a square in general, that's going to be s squared. Now I have to find a way of defining the side of this square in terms of x. So if we look back at our graph, these squares are growing out of this base region here, this region R, and the side of each square is just the distance between the x-axis and this exponential function. So we can define the side of a square as this function right here, e to the negative x squared over 2. That will give you the base of the square, or the side of the square. So I'm just going to rewrite this with all of this stuff squared. That's my a of x. And now my volume, I'm going to have the integral from, let's see here, we were going from the y-axis to x equals 3. So that's going to be from 0 to 3. So integral from 0 to 3 of this a of x dx that I just wrote. Let me do the rest on the calculator now. So it's time for an integral. Let me do math 9. I'm going from 0 to 3. And the a of x in here that I'm actually integrating is this thing here, which when you get down to it, I already stored the stuff here that's being squared as y1. This was the original function. So I'm just going to take y1, so alpha trace y1, and square that. And then I'll just do dx here, press enter, and hope for the best. Comes out to about 0.886, which gives me answer choice A. For this problem, region bounded by the graph of y equals 2x minus x squared and the x-axis is the base of a solid. And for this solid, each cross-section perpendicular to the x-axis is an equilateral triangle. What's the volume of the solid? So let me graph this out first to see what we're looking at. So I've entered that function in my y equals. Let me do zoom 6. All right, so let me zoom in a little bit more. Zoom 4 probably is a better one to use. There we go. So we have this little region in here between 2x minus x squared and the x-axis, and we've got some equilateral triangles growing out of this thing. So I need to find the volume of the shape that transpires when that happens. So for this is one of those known cross-section problems. You really just need to take the integral of the area of the shape from one x value to another, and we'll talk about the limits of integration in just a bit, but let's get the shape first, the cross-section shape. That's going to be a triangle. It's going to be an equilateral triangle, and this is going to be a little bit tricky. In general, 1/2 base times height is our triangle formula, but it's kind of hard to talk about equilateral triangles in terms of base times height. So here's an equilateral triangle. It's the same side on all sides, so I'm going to write S everywhere. And this side down here, this is actually the base of these triangles. That's the distance between the x-axis and this 2x minus x squared function. So we actually have a way of defining this base here in terms of the x values. The trouble is defining height in terms of that. So if we can at least rewrite the height in terms of s, we can then plug in 2x minus x squared for s and come up with a formula that covers everything. So let's talk about the height. If I drop an altitude here, that splits this into two of these 30, this is a 30, 60, 90 triangle. And you might remember from your geometry days that this has a ratio of s radical 3, 2s. So that means that this 30-degree side down here is going to be, since this whole side is s and we're cutting this in half, this is going to be s over 2. And since this right here is the s from this formula, that means this 60-degree side is going to be whatever this is times radical 3. So this height here is going to be equivalent to s radical 3 over 2. So when I rewrite my triangle area formula, which is initially 1/2 base times height, in terms of s, I'm going to rewrite this as 1/2 times the base s times the height of s radical 3 over 2. And that's a little bit of a mess. I'm going to simplify this a little bit here as this will be 1/4, and we'll have an s squared radical 3 on top. So s squared root 3 over 4. Now we said just a moment ago that this s here, going back to our graph, the base of this equilateral triangle was really just the distance between the x-axis and 2x minus x squared. So I can rewrite this whole thing as 2x minus x squared quantity squared times radical 3 over 4. So that was just kind of a mess, but that's where this formula is coming from, is doing a lot of analysis to get the height and the base in terms of the same variable with equilateral triangles. Okay, so we've done all that. Now we need to know what our limits of integration are. So we need to know where this function intersects the x-axis, where it equals 0. And that's actually not so hard to find. We can just factor out an x here, leaving us with 2 minus x. So that gives us limits of integration of 0 and 2, which you could probably see just by looking at the graph. So now my volume is going to be the integral from 0 to 2 of this a of x that I just defined. And now I'm going to have to do all of this on the calculator. To try to make this a little bit cleaner, I'm going to put my whole a of x function here in y2, and then I can just integrate y2 from 0 to 2 in my integral. So for all of this, I'm going to need a fancy fraction here. So let me do alpha y equals n over d mode. And in the numerator, I have this 2x minus x squared business being squared. Now 2x minus x squared, that's actually my y1 that I graphed earlier. So I'm just going to do alpha trace y1 and square that. So that's a little bit cleaner than what I could have written. Now I'm going to multiply that by radical 3. So there we go, radical 3. I'm going to have a 4 in my denominator. And there's my area function. So let's quit out of there now. And let me do math 9 for my integral. I'm going from 0 to 2. And let me do alpha trace y2 now, because that's where I just stored that crazy a of x function. Put an x next to the dx, press enter, and after all that we get 0.462, which is going to be answer choice D. So for those of you who have already checked out my other solution for this problem with the cross-section perpendicular being an equilateral triangle, and you didn't like that other solution with the special right triangles and all that stuff, here's an alternate solution. So I'm assuming you already watched that other solution for this to make any sense. So here's our triangle again. All sides are the same. And instead of dropping an altitude and trying to define the height in terms of s with special right triangles, another way you could go about this is using the half sine area formula. That's 1/2 AB sine C that we can let a of x equal. And the a and b, basically you have some angle that you know, and a and b are the two legs of that angle, and c is just the angle itself. So a and b are both s's based on this setup, and c is the angle right here, which can only be one number. This is an equilateral triangle, so all the angles are going to be 60 degrees. But this is calculus, and we do everything in radians, so I'm going to write 1/2 sine, or s squared sine of pi over 3. And instead of writing s squared, we said earlier in my other version of this solution that 2x minus x squared was really giving you that distance in terms of x. So we 1/2 that stuff squared times sine of pi over 3. And if you think about it, sine of pi over 3 is just radical 3 over 2. If you multiply that by the 1/2, you still end up with this stuff squared times radical 3 over 4. It's just another way of getting there. So just like before, setting this equal to 0 to get the limits of integration, we can factor out an x. We get the limits are 0 and 2. And doing my integral from 0 to 2 of this formula here, I'll just show you on my calculator to prove it comes out to the same thing. So in my calculator this time around, in y3, I'm going to enter this alternate formula. So 1/2. There's 1, there's a 2. And then we're still going to do alpha trace y1 and square that. But now I'm going to do sine of, let me get my fraction back, pi over 3. And close the parentheses. Let's quit out of there. And now let me yank my integral from before, my other version of this problem. Instead of y2, let me do alpha trace y3 to put in this alternate formula. And we see that we end up with the exact same thing. So just another way of getting there if you remembered your half sine formula. For this problem, we're told R is the region in a first quadrant bounded by y equals x squared below and above by y equals radical x. And then this is actually the base of a solid whose cross-sections perpendicular to the x-axis are squares. We want the volume of that solid. Let me start by graphing this out since I am allowed to use a grapher on this. So in y1, I've got my x squared. In y2, I've got the radical x that they were talking about over there. And graphing those out, I'm just going to do zoom 4. These are pretty close together here. So I've got this little sliver of a region in here. And I'll zoom in even more, I think. Let me do a window from, let's just do 0 to 1.5. And let me zoom fit that. 1.5, zoom 0. So there's my parabola, there's my square root function. Okay, now I can see this a little bit better. So we have some squares coming out of here. In general, the formula for the area of a square, which we're going to need for our integral on this, is going to be s squared. So in particular, relating that to x, the side of each square, these squares are coming out like this. So this is a square going from like the top to bottom of this region here. The side of the square is just the distance between these functions. So that's going to be expressed by, this is radical x minus x squared. So I'm going to write radical x minus x squared squared, and then that's going to be my area function. So now I'm just going to integrate that from, well, let's see, where do these intersect? It looks like they intersect at 0 and also at 1, and we can double check here. If you plug 1 into radical x and x squared, you get 1 back, so they definitely intersect there. And I guess you could set them equal to each other, square both sides, and you see that 0 and 1 are the places that they end up intersecting if you do all the crazy algebra on this. So anyway, not to belabor that point, we have our volume being the integral from 0 to 1 then of this a of x that we just defined. And I'll put a little dx in there as well. So let me do that on the calculator. Quit out of there. So I've got, let's see here, Math 9, and we're going from 0 to 1. And I'm going to have to open a parentheses in here. So I'm going to have radical x. Now radical x, I guess I could do the alpha trace y menu, but let me just put in radical x directly. There's no need to get too fancy on this. And then we've got minus x squared, close my parentheses, square all of that, and dx, and that's going to come out to 0.129. And that ends up being choice A.